is Bahman Tohidi. I want to present a new concept, Intelligent Hydrate Management, that I believe is an effective step towards net zero emission. And I believe that we won't have any more hydrate blockage in the industry if we implement this solution. Now, what are the aims and objectives of Intelligent Hydrate Management? Is avoid hydrate formation altogether. Alternatively, hydrate, as long as it doesn't cause blockage, is not a problem. So accept some hydrate formation while avoiding hydrate blockage could be a solution. Obviously, we want to minimize inhibitor usage, but at the same time, we want to make sure we have enough inhibitor. Reduce or eliminate the effect of oil and gas activity on the environment. Also, it can also monitor hydrate dissociation. And the next step would be to develop an integrated monitoring system. And finally, we can integrate this with IIoT, Industrial Internet of Things. So, starting from beginning, condition for hydrate formation is presence of water or ice. Suitable size molecule, can be gas or liquid molecules like C1, C2, C3, IC4, NC4, CO2. And the other requirement is suitable pressure and temperature condition. This suitable temperature and pressure condition is a function of two parameters. One, hydrocarbon composition. Two, aqueous phase composition. For hydrocarbon composition, as you know, two molecules can have attraction toward each other. And here we are showing the attraction, and this is the distance. If the molecules are far away, they have no attraction or repulsion. So the energy level is zero. When they get close to each other, there will be a shift in hydrogen clouds. So part of the molecule become positive and part of it would be negative. So they attract each other. When they get too close to each other, they will repel each other. In a hydrate, it is a crystalline structure, like here. You have oxygen and hydrogen, oxygen and hydrogen. And the two molecules, one is this oxygen and the other one is the gas molecule. the molecule that get trapped in hydrate structure. How far they are from each other is mainly a function of the size of and shape of the molecules. So if the molecule is very small, like hydrogen, they are far away and they don't have a lot of attraction. But if molecule also too big, they will fall here. They repel each other. So a certain size of molecule create the maximum attraction. And that will promote hydrate formation. So you see that the hydrate phase boundary is a function of the gas molecule. And I said that the other factor is composition of water phase. Anything dissolved in water will reduce activity of water and makes less water molecule available for hydrate formation. We use this technique for preventing hydrate formation by injecting glycol and alcohols. Glycol or alcohol dissolve in water. Some water molecule will be busy with the solution of this molecule. Therefore, less water molecule are available for hydrate formation. So this is a common technique in the industry to avoid hydrate formation. If you inject too much inhibitor, the curve moves to the left. And if you don't inject enough inhibitor, then consequently it will be on the right side and increasing the risk of hydrate formation. Here, let's see if I can show this video. You can see that this is the high pressure glass window and hydrates form at the water and gas interface, and the layer of water on the gas phase forming hydrate, and the layer of hydrate preventing mass transfer into water, so the water is liquid water. And the fact is that the water is still liquid, means that it's not ice, it's hydrate. How to evaluate risk of hydrate? We need to determine the hydrate phase boundary. And you know that the hydrate phase boundary is this one, for example. And we need to know the composition of hydrocarbon phase and aqueous phase. Hydrocarbon phase does not change much, but aqueous phase can change very quickly. And we put 3 to 5 degree safety margin. So if I assume 3 to 5 degrees safety margin, then I need to shift the curve to the right. Pipeline condition. This will show water pipeline condition. So pipeline, the fluid is initially warm and cool down like deep ocean, and then when it comes to surface, then or shallow water, it warm up. So how do we determine this? By modeling or pressure and temperature gauges, or just assume the worst condition. The worst condition would be maximum pressure of the pipeline and minimum seabed temperature. So we add a safety margin, we can add to the hydrate phase boundary, or we can add it to pipeline condition. One of them is enough. And then we superimpose the two figures. So if you superimpose the two figures together, we get something like this. This is a sort of simulation of Omberlanga in Norway when the water depth is around 950 or 1,000 meters, and the fluid comes to the manifold and and to the manifold, and then climb the continental shelf, shallow water, and then warm up. And this is downstream condition. So although inlet and outlets are outside hydrate phase boundary, it is possible that some part of the pipeline are inside hydrate phase boundary. So in general, we want to avoid hydrate formation. One is water removal. This is the very good option. However, it needs dehydration, and dehydration is very expensive for an offshore reservoir. Another option is to control system temperature. If you use insulation or effective heating, then we can keep the pipeline temperature above hydrate or to the right of hydrate phase boundary, outside that. Another theoretical approach is that to reduce pipeline pressure. The problem with pressure is that pressure is the energy of the reservoir. And we don't want to waste that energy. So normally reduction in pressure or depressurization is used when we have a blockage and we want to get rid of that blockage. Another option is to inject thermodynamic inhibitor, like methanol, ethanol, glycol, etc. That in effect shift the hydrate phase boundary to the left. It can go somewhere here, prevent hydrate formation. The other option is to use kinetic hydrate inhibitor. Kinetic hydrate inhibitor work with the hydrate structure. So they will stick to this hydrate, the initial hydrate formation, and prevent its growth, affect the kinetic of the process. Another option is that to use antiagglomerant. Antiagglomerant do not prevent hydrate formation, and some of them maybe promote hydrate formation, but they prevent hydrate crystal to stick to each other. And another option is cold flow. Cold flow is that we don't use heat, we don't use insulation, and reform hydrate, but control the hydrate formation or the amount of hydrates formed that do not result in a blockage. This came for offshore reservoirs at the cost of insulated pipeline or direct heating was high. We can also use various combinations of the above. For example, we can use some inhibitor like methanol plus some KHI. You might have salt in the system, use some glycol. We can have the system under inhibitor and use cold flow. So there are various options to combine them together. So in the life of a reservoir, what changes can we expect? It's possible that in the life of reservoir or even daily, minimum ambient and pipeline temperature changes. So if that changes, means that you need more or less inhibitor. Also, after production, for a while, reservoir pressure will be reduced. That will affect the pipeline pressure or the residence time. At how long the pipeline will be in the hydrate region, or how long will it take for the fluid to pass through the pipeline. Another important changes is the water cut changes. It basically would affect inhibitor concentration. It is also possible that initially we have condensed water, after a while we have formation water. Formation water normally has some salt, but condensed water could be almost salt-free. Another possibility is that inhibitor partitioning between different phases will change. For thermodynamic inhibitor, the amount of inhibitor in the aqueous phase is important. So if that changes, it will change the concentration. It is also possible that pump does not work properly. And human error is another possibility. In fact, these two, pump malfunction and human error, are probably the most important cause or causes in previous blockage. It is also that the inhibitor, because for example, MEG regeneration unit, the specification of leaving MEG regeneration unit or lean MEG can change. Therefore, if you are injecting a certain amount of inhibitor, if the concentration of effective chemical changes, the condensation of chemical will change, and that could result in hydrate formation, and etc. What industry uses? In fact, these are normally designed by consultants. In the feed stage, they don't want to take any risk, and they design the inhibitor for maximum pressure and minimum temperature, normally over the last 100 years. And that would be somewhere here, while the pipeline condition is here. So we over-design inhibitor. And during production, as we say, that the pressure can drop, they don't change the inhibitor injection rate. So the design of inhibitor is based on minimum pressure, maximum pressure and minimum temperature, and maximum residence time. So you see that some companies say that test this inhibitor for 96 hours, for example. And in addition to that, they take an extra 10 to 30% for potential bad mixing. Normally we use too much inhibitor. And unfortunately, the still overusing inhibitor blockage will happen because we are not monitoring. And too much inhibitor can result in other reassurance problems. For example, too much alcohol in a salty water can result in salt deposition. Like here. This is a picture of inside the well bore that they were using initially. They only had condensed water, so we're using methanol. After a while, formation water started production, and still they continue using methanol. While the formation water had salt, salt is a hydrate inhibitor. They should have taken that into account. Now, when salt, so therefore here, salt and methanol are competing for water. And in such a competition, alcohol will win because salt is soluble, alcohol is miscible. You can dissolve up to 20–25% NaCl in water, depending on the temperature. But you can dissolve 100% methanol in water. So if you overdose methanol, will result in salt deposition. So in effect, if we want to be more realistic, our residence time start not from here, from the point here, the system enter hydrate formation. And then exit hydrate formation region. And if you want to be very accurate, you should observe the subcooling. Initially, subcooling is very little, and here subcooling is maximum. And furthermore, if you want to be more realistic, you need to design the changes in reservoir. This is reservoir pressure, and that changes with time. So flow line condition will change. And then after a while, you need to reduce the pressure of separator. So the new flow line is like this, pressure and temperature. And we don't take these into account. So in order to increase the reliability of hydrate prevention technique, minimize and optimize inhibitor injection, we can have developed a system like this. This is hydrate phase boundary. This is pipeline condition. And ideally, we want to have a safety margin. We need to have a safety margin. Pipeline condition shouldn't be too difficult. We can use computer simulation. For determining hydrate phase boundary, as we said before, you need the composition of hydrocarbon phase that doesn't change much with time, and you need to have the composition of aqueous phase. You need to know the amount of salt and chemical hydrate inhibitor. And we told in the industry, we take the sample. The problem is that it takes a long time to send the sample to the lab and takes time to test it and get the results in the field. And that could be too late. So what is intelligent hydrate management? Minimize, eliminate the chemical while reducing risk of hydrate blockage. Reducing carbon footprint of the oil industry, and this would be a step, an important step towards zero emission objective. How is it possible? So if you monitor hydrate safety margin, like I explained here, this is safety margin, you can monitor this, and we achieve this. Also, if we have a system that detect early signs of hydrate formation and providing an early warning against hydrate blockage, that is ideal. Another extra safety factor that the industry so far do not take into account, that we forget that what is important is blockage, not hydrate formation. We can, if we have some hydrate, we can melt them on surface, but in general, when it comes to shallow water, temperature is higher and then they can melt themselves, or we take that into account of how much hydrate we can transport. So transportability of hydrate really is an important factor. The hydrate formation is an exothermic process. So a lot of heat is released when hydrates form. And that will take the system outside hydrate phase down. So that heat transfer is very important. At the moment, we don't take much attention to the rate of hydrate formation. And I've done some calculation for different systems. We can calculate this very accurately. We can also monitor pressure and temperature system and providing the necessary action to minimize the risk of blockage. And finally, you can develop a database and machine learning system. In the unlikely event of hydrate blockage, we are all ready. And as I discuss later, if we are ready and implement hydrate remediation technique, we have less hydrate to deal with. As normally, hydrate blockage gets harder with time. So here an example is the micro model. We have formed hydrate 31 hours before. Water is blue, hydrate is white, and here you see that although some hydrate has formed, there are some water within hydrate region. After 94 hours, you see that the extent of hydrates has increased. Here. And the amount of hydrates here has increased. Because water normally does not have enough gas to completely become hydrate. So the gas should migrate from different parts of the system to contribute to hydrate formation. And this is after 142 hours. Yeah. When you think about the hydrate in nature, they had a lot of time to form hydrate. So that's why it is solid hydrate. It could be solid hydrate. We will even uplift sediment to form hydrate. So the sooner we tackle hydrate issues, the less hydrate we will have. So minimize, eliminate hydrate inhibitor to protect environment and chemical and CO2. But then we need less production of chemical and less CO2 production. Reduce and eliminate CAPEX and OPEX. If you reduce the chemical, operational costs will be reduced. If you reduce the size of the storage or size of inhibitor, regeneration, CAPEX will be. So, and also the overall economy will improve because you don't block. Each time you block the pipeline can be a long time. You need to find a way to remove blockage and the cost and the danger, and also the deferred production. So the outcome of the intelligent hydrate management, more economical, more environmentally friendly, and more reliable operation, and move towards automation and IIO. How is this possible? How can we do this? A device we have developed, HydraCHEK, is a device that determines and measures the composition of water phase in 5 seconds. So we take sample. We don't need to send you to lab. It is a vessel, 100 cc sample, and within 5 seconds, pressing a button will give you the amount of water, amount of salt, and amount of chemical inhibitor. And then you know the hydrocarbon composition, you can determine the hydrophase boundary. And knowing the pipeline pressure and temperature condition, we can determine the hydrate safety margin. This device has been implemented in many places around the world. And HERIOT WATE has won the Queen's Anniversary Award because of one major important was the company Tohdi was able to reduce the amount of inhibitor from 28% to 0 and extend the life of the reservoir by 5 years. This has been applied also in Central Asia and many other Persian Gulf, Qatar, many other places, and very successful, and they protect the environment and increase production and reliability. So this device, basically, this is a conductivity meter. We also measure temperature here. This is velocity meter to faucet and receiver. And we take 100 cc sample here. And within 5 seconds, the system will give you the amount of salt, KHI, inhibitor, methanol, whatever. So if you want to see how it is done, you can look at this video. Now, so imagine that you have a separator or a spot catcher, and fluid comes here, the gas will leave from here, oil here, and water come down with the water degasser. You take a water sample, put your device, and determine the hydrate phase boundary. So the other important device that we have is HydraSENS. HydraSENS detect early signs of hydrate formation. As you know, as we discussed earlier, the big and spherical molecules have higher tendency for hydrate formation. For example, if the system is structure 2 system, then IC4 and propane will be depleted from the gas phase. And because the gas phase is the fastest moving phase, detection is very quick. We can also estimate the location of hydrate formation, which would be very useful in deciding what option we choose in removing or preventing hydrate formation. This is a field trial, has been field trial by Total, and you can look at this, or if you don't have it, I can send it to you. You can use here the test and field trial, and this was a case that we have very high GOR system and 14,000, and they were using anti-agglomerant, and the result shows that only 10 days in the year they had the risk of hydrate formation. This is HydraSENS. You see me here, and the whole prototype is here. On non-GC, gas conditioning, water removal, and here forming hydrate lab. So it works. If you need more information, please contact me. And this is the field trial. So in this case, we have a separator, sample the gas, and see the ratio in this case, because structure 2, C1 to C3, and C1 to C4. So anytime hydrates form, C1 is reduced from gas phase. That will result in C3 is reduced from the gas phase. That will result in C1 to increase. So hydrate formation, this ratio will increase. The same happened with IC4, because IC4 is easy to form hydrate. So when hydrates form, IC4 is used from gas phase, goes to liquid phase, because hydrate density and water density are very close to each other. And as a result, the reduction in the amount of IC4 will result in an increase in the C1. So you see that they are matching each other. So here you see that goes up means hydrate is forming, go down, hydrate is melting, here is forming, here is melting. And after further analysis, we notice that hydrate is forming during nighttime and melting during daytime in the pipeline. The separator is not only 10 days. You can also, as I said, you can locate where hydrate is formed. So a system like this, you get the sample of the gas phase, and you also get the sample of gas released from hydrate. And initially, when hydrate forms, heavy component concentration in the gas phase will be reduced. So you see that in the gas phase analysis, because gas is moving the fastest phase. So you see that. What happened to hydrate? Hydrate density of water. Hydrate is very close to density of water. So it will fall in the water phase, and we look at the gas released from water phase. And first of all, the amount of gas should be increased because hydrate will store a lot of gas, but also here you should see high concentration of C3 and IC4. So if you time this one at time 0 and this one after 1000 seconds, and you have information about the slip velocity. Slip velocity is the velocity difference between gas and liquid phase. For example, gas phase is moving at 15 meters per second, liquid moving gas phase 15 meters per second, water is 5 meters per second, so its slip velocity is 10 meters per second. So if the difference between two signals is 1000 seconds, means that hydrate is forming at 10 kilometers away. Combining HydraCHEK with HydraSENS will provide a very powerful device to avoid hydrate formation. HydraCHEK detect hydrate phase boundary, and obviously we can, by minimizing inhibitor, we can get as close as possible to hydrate phase boundary. If there is an error or sudden change, the HydraSENS is there to detect early signs of hydrate formation. And a combined system will look like this. HydraCHEK is here, as from the water phase, and HydraSENS here, monitoring the gas phase and the gas released from hydrate. So we can detect if there is something goes wrong and hydrates form, and we can estimate slip velocity and can detect where this hydrate is forming and indicate the necessary action to prevent pipeline blockage. In the very unlikely case of hydrate blockage, it is ideally you have to act very quickly. As I mentioned earlier on, the sooner you tackle hydrate, the better, because hydrate gets harder. And we can detect how hydrate is melting by using HydraSENS, and HydraCHEK can give an estimate of water converting to hydrate, and thermal calculation will tell us how long will it take to hydrate, the form hydrate to melt. In conclusion, we can address hydrate problem, and we don't expect any future hydrate blockage if this technique is applied. And this is possible because of the new equipment, HydraCHEK and HydraSENS, and also advances software, HydraFlash, and better understanding the effect of heat transfer and rheology of hydrate system. Basically, all these techniques have been tested previously We want to combine them together. The final product will be able to minimize inhibitor injection rate while increasing reliability, hydrate prevention strategy. The reduced injection rate, avoiding hydrate blockage, removing the cost association with hydrate blockage, depressurization, extra chemical, delay production, damage to product equipment, flaring, injury, they all can be helped. And these are major effects or steps towards zero emission. Okay. That's enough for today. Thank you very much for your attention. Thank you.